Concurrency. So we talked about optimistic concurrency before. I think there was some question about commits and rollbacks and how this whole thing works. So let's get into that a little bit. So optimistic concurrency controls is something that comes built into the Iceberg table. Traditionally, it's something you would have had to develop on your own using like a DynamoDB database to lock transactions and stuff like that. But Iceberg comes with this optimistic approach. And what does optimistic concurrency actually mean? It basically means that it tries to create or update tables optimistically, basically assuming that this particular operation lives in its own little world and nobody else is doing anything, and I'm just going to put my blinders on and I'm going to do my thing, right? So the way it does it, it basically takes a snapshot, takes the latest snapshot and says, I'm just going to work within the context of this snapshot. So according to me, nothing around changed, it's just this. And then I'm going to make changes. I'm going to apply changes. I'm going to create my manifest files. I'm going to create my Parquet files, and then I'm going to try to commit. And the way that I'm trying to commit is by swapping the metadata file, right? That first file I showed you, changing that in the catalog. So if the catalog is pointing to metadata file number 1, after I've made changes, I'm going to update the catalog and say, hey, catalog, go make changes by swapping the metadata to metadata 2. Now, so it points to my latest copy, right? And that's optimistic. And if it breaks because somebody else made a change and already changed the pointer in a catalog, I will see that when I try to change it, then I will fail. I will say, okay, this doesn't work. And there's really two ways to do it. There's 2 isolation configurations you can have. The first one is serializable isolation, and this really guarantees that transaction kind of behave as if they're executed in a serial manner. So that gives you full control. It gives you more consistency and predictability of the behavior. So if you're making a lot of changes and other systems are making changes, it operates as if it was done serially. So, one is done, second one's done, third is done. Nobody steps on top of each other, right? The problem with that, the downside to that is that it's much slower. It lowers the concurrency because it goes slower. You have to check everything. So you can run concurrent queries or concurrent writes as frequent as you want. And there's potentially higher rates of transaction failures and retries, right? Because you're almost bound, if you have a lot of writes at the same time, you're bound to conflict, and then you'll fail, and then you have to retry. So you end up seeing a lot of that. The other one is snapshot isolation. So the snapshot isolation is the most common one. You'll typically see that being configured as the default. The way that's handled is basically it allows concurrent transaction to take a snapshot. Each one of them take a snapshot of the table and says, I'm going to operate on the snapshot. And when I'm done, I'm going to swap the pointer in a catalog to point to my snapshot. Now, if that fails, because like I said before, the snapshot already been advanced by another user or by another engine, then I will just try again. Or I will see, hey, what changed? Can I still apply my changes, or are they overlapping with the changes that somebody else made? If they're overlapping, I'm going to fail, and I'm going to let the user figure out what the problem was. If they're not overlapping and they're kind of like can operate on their own, then I will just reapply my updates, create a newer snapshot, and advance the table that way. All right. Now, it's good because there's high concurrency. You can actually support multiple writers all operating very fast and doing stuff. So the concurrency is much higher. The downside is you end up with more storage. You end up creating a bunch of snapshots and a bunch of manifest files. But it's okay. There's tools, there's this mechanism to clean that up, but kind of do take that into consideration. And then there's some kind of these called like non-serializable anomalies. Like if your engine is reading this latest snapshot and you're trying to switch it, but something happened and you didn't quite complete, and then the user tried to rerun the query and they're not seeing the proper snapshot. So there's a bunch of things like that. They don't really happen very often, but you can run into kind of these inconsistencies when you do snapshot isolation, because it's fairly naive. It's fairly optimistic. Well, it is optimistic. Cool. One second, this question here. How does the transaction commit and rollback happen with Iceberg? And how are the transaction locks handled, if at all? Right. So kind of like what I was saying before, when you make the commit, whichever isolation you have, if you make the commit and that commit fails, then you'll typically retry. If you try to make the commit, but there's an overlap, you're trying to change a row that somebody else already changed, then that typically would fail, and then you'd have to fix it. You'd have to figure out like what went wrong and then how to fix it. There is a locking mechanism in Iceberg, so you can use a DynamoDB lock server to actually introduce locks into the system. I don't go into detail here. You can read about it on the documentation. It's a bit more heavyweight, more configuration, more things to worry about. It is a little bit slower just because you have to keep taking lock. But if you have multiple systems that are constantly writing at high volume and you really want that consistency, then that could be an option for you. So does Iceberg considers read after write consistency? So again, it's based on the snapshot. So if a user is now running a query against Iceberg, it looks at the latest snapshot, it gets the manifest, and then it scans the files, and that's all you get. If somebody makes a change behind the scenes, so while your query is running, somebody's making a change behind the scenes and adding files, creating new snapshots. As a query is running, it's not going to know, right? It's going to still operate on a snapshot that it took. It may be 1 or 2 or 3 snapshots behind, but that's okay. It just lives inside that bubble. So it doesn't know of anything new. Once the snapshot has been committed, that's it. Then all the data is available. Everybody can see it, right? So there's no, basically like if the snapshot's committed, the files themselves are visible through the manifests. So then you get this read after write consistency. So once you commit, you wrote the snapshot, you switch the pointer in the catalog. Now all the data you just wrote becomes readable, right? So it's not like you committed and then some files will later be read. No, once you make that switch in the catalog, all those changes, all those files become readable right away. Okay, so what does concurrency control actually looks like? I was going to run a test, but I'm kind of running short on time. So a couple of things you'll see in your logs. So the first one, if you're enabling serializable isolation, you'll see the first error kind of tells you have found conflicting files that can contain records matching this file. So it tells you, hey, you're trying to change data that conflicts with this data I found in this file over here. Go figure it out and fix it. You may retry. You'll retry a few times and then eventually it'll fail if it can't resolve it. When the snapshot isolation just tell you, hey, glue detected concurrent update, right? Somebody's trying to change the pointer, right? The snapshot in the catalog, trying to change it while you're trying to change it. So how do you deal with it? You can update your table. 3 different main properties. There's others in documentation you can look at, but the main one is the write merge isolation level. So pick snapshot over serializable if you want high concurrency. Also tweak the retries. So retrying number of retries, I put 10 here, fairly low. If you expect a lot of changes or high volume of data, you may want to increase that. Minimum wait time in milliseconds. Again, you want to tweak and tune that based on what your properties are.